Right, so in this video I'm going to attempt to, in 10 minutes, run through what I would have done in around 6 lessons and just reiterate the important points from the groups topic. So it starts off with alkali metals. You need to know their physical and chemical properties, and a question they love to ask is the physical properties that are unique to the group 1 metals, and that will be a relatively low melting point and the fact that they're soft. If you don't have the word relatively, you don't have the mark. You can't say their melting points are low, but you can say that they're low compared to other metals. Also, the fact that they're soft enough to cut with a knife, that's a unique property of an alkali metal. The other metals don't have that. In terms of chemical properties, you're looking at how they react. To do that, if you remember, you would have taken the alkali metals and thrown them into a large trough of water, and you have to explain what you see and then just describe the trends in reactivity as you go down the group. A few points: we used a large trough of water because this is a very exothermic reaction. The large volume of water can absorb all of that extra heat that is given out. That's why we use a large trough. It's a safety point. You wouldn't handle the metal with your hands. You would wear gloves. You would also use a tweezers. The metals themselves are stored under oil. They're so reactive that they would react with air and oxygen if they weren't stored under oil. You use a tweezers, you chuck it in the water, and then you note your observations. So in terms of what actually happens, you're going to form the metal hydroxide and you're going to form hydrogen gas. All right, often people just forget that that's the product that's formed. So lithium hydroxide or potassium hydroxide, which depending on the metal that you've used, and you're forming hydrogen gas. In terms of what you see, because I've asked you to explain, you need to tell me why you see it. So you'll see them floating across the surface of the water. They don't sink, and that's because they're less dense than water. You can also say that they fizz or bubble or effervesce because they're producing hydrogen gas. If you were doing this with potassium, you'd obviously be forming potassium hydroxide. You would see a purple flame in this case, but to prove you're producing potassium hydroxide, because they're alkalis, you'd use an indicator. So I've used universal indicator here, which will turn blue, and the hydrogen gas test is just lit, splint, squeaky, pop. Halogens is maybe a little bit harder, so I'm going to go through this in slightly more detail. So this 6 marker has come up twice before. How can you use displacement reaction? So design your own experiment essentially to show that they get less reactive going down the group. So I've just written them in order here: chlorine to bromine to iodine. They're getting less reactive, so I need to prove using a displacement reaction that chlorine is more reactive than bromine, and I'm asked to include an equation, and I'm asked to include an observation. Okay, so if I want to prove that chlorine's more reactive than bromine, then chlorine has to be by itself and bromine needs to be bonded to something, and typically we will bond it to a group 1 metal. So I'm going to take sodium. So sodium and bromine are bonded together. Sodium's +1, bromine's -1, so that's my sodium bromide. And I need to remember that chlorine by itself is diatomic. So I'm going to take chlorine and I'm going to react it with sodium bromide. Now when I'm doing this, everything is going to be in solution, and that means my state symbol is going to be AQ and my state symbol here is going to be AQ. And because chlorine is more reactive than bromine, it displaces it. So I form sodium chloride, again it's going to be AQ, and I form bromine. Again, it's going to be AQ. So that will be my balanced equation. I have to give an observation. This is a color change, all right? You'll see I don't have any G. That means I'm not seeing effervescence. And you need to know their colors in solution. So chlorine in solution is just colorless, and bromine in solution is orange. So you're looking at the halogen in solution that is by itself. So it's going to go from colorless to orange. And then what conclusion can I make from this? I can say that chlorine is more reactive than bromine, therefore it displaces bromine. Okay, that's my conclusion. That shows that chlorine is more reactive than bromine. I'm now going to show that bromine is more reactive than iodine. Do exactly the same thing. If this is the one that's more reactive, this is the one that starts by itself. Again, it's diatomic. Again, it's going to be aqueous. I'm going to bond iodine to something. You can use lithium iodide, sodium iodide, potassium iodide, whatever you want. NaI, also going to be aqueous. Bromine takes iodine's place. just realised now I haven't balanced the one above, and I get sodium bromide, and then iodine is left by itself, and everything's going to be aqueous. Apologies, 2, 2, 2, 2. That is now a balanced equation. And again, I need to say what I'll see. So bromine, just as I had over here, when it's by itself is orange, and iodine by itself is brown. So I'm going to see a colour change from orange to brown, and the reason I see this is because bromine's more reactive than iodine, so can displace it. I don't need to do another one with chlorine and iodine. If I've shown that chlorine's more reactive than bromine, and bromine's more reactive than iodine, then it goes without saying that chlorine is more reactive than iodine. You also don't need to do other combinations and show that it doesn't work. You can answer this question just using 2 equations and 2 observations, so you're kind of wasting your time by writing more. You need chlorine versus bromine, bromine versus iodine, colour change for both, and then just a conclusion, and you'll get all of your 6 marks on that. The last one, why are they redox reactions? They asked this last year, and they were quite kind of pernickety about the phrasing. So again, anytime you're asked to explain why something is redox, just give the half equations, because that avoids you falling into the pitfalls of calling them ions and calling them elements and all the rest of it. So if you're being asked why something is redox, I would start by explaining what redox is, okay, because that can often be a point in the mark scheme. In a redox reaction, okay, oxidation and reduction both occur. So that's what a redox reaction is, and I would state that oxidation and reduction occur, and then you need to show me what's oxidized and show me what's reduced. So if I go back and use one of these as a guide, I'm just going to work out what's being oxidized and what's being reduced. So if I look at bromine here, it starts off as Br2, and on the other side I can see it's part of an ionic compound, and it's going to be present as 2Br minus. Now to get from Br2 to 2Br minus, it must have gained electrons because it's becoming negatively charged. So I can write Br2 plus 2 electrons goes to 2Br minus, and I can say here that this is an example of reduction. Going to look for an example of oxidation then. If bromine is being reduced, then iodine must be being oxidized. So if I look here, I'm starting off with it in an ionic compound. It's got a negative charge. There are 2 of them, so 2I minus. And then on the other side, I can see it's just present as I2. So it was negatively charged. Now it's got no charge at all. So it's losing electrons. And that would be an example of oxidation. Now, if you had attempted to write that in words and you didn't call that the iodide ion, you would lose your marks. And that's why using the half equations, if you can write them, just avoids those pitfalls completely. So please, anytime you're asked for redox or showing something's oxidized or reduced, just write the half equations. It will always get you your marks, even if it's not asked for it.